You know, I was going to start with an NTP joke, but I can never get the timing right. Okay, never mind. Yeah, boo, boo, boo. Okay, my name's Alex Schoof. I'm a principal engineer at Fugue. We build software to help you manage the deployment and operations of really large and complex infrastructure, especially infrastructure that's running in cloud environments like AWS or some other places. And before that, I spent a number of years working on the security team for a very large online bookstore that also happens to rent servers by the hour. I've also spent time working at a number of, startups and other large enterprises. And something that I've noticed in all of these places that I'm sure you all have noticed too is that secrets are everywhere. It seems like in a modern application or some modern infrastructure, you have secrets just littered across the infrastructure. And there are secrets that we notice every day, things like the production database password or an SSH private key. But there are also a lot of secrets that maybe we don't think about. You know, there might be that third-party API key, or if you're using a modern MVC web framework, there's probably a string buried somewhere in a config file that controls how your session tokens are generated. And mishandling secrets can be very, very bad. The level of badness here can range from a minor operational annoyance up to and including business-ending events. But in spite of this, as an industry, we seem to be really, really bad at managing secrets. It seems like every week you hear a new story about somebody, you know, checking AWS creds into GitHub, or, you know, an engineer leaves the company, but they still have access to corporate Dropbox that has, you know, the production decryption key, and then you leak a whole bunch of PHI all over the internet. And there's a lot of reasons why this can happen, why you can lose control of your secrets. But I think the root cause here is that while we've spent the last several years as an industry trying to adopt and push automated, hands-free, very robust systems to build and deploy and test our software, we really haven't spent that much time thinking about secrets. In fact, I would assert that we tend to manage secrets the same way we tell people not to manage software. What I mean by that is if I told you that I had a large production-facing web application and my deployment story involved me SCPing tarballs across my fleet and manually logging into every host and configuring each instance of Apache or Nginx, you'd think I was insane. Why would I ever do that? I'm going to not sleep at any time. You know, I'm delivering horrible business value and agility. But that's actually not far off from how a lot of people manage secrets today. So I think it's time that secret management is part of core infrastructure. The same way that when a developer starts something as a prototype and moves through all the way to production, we expect them to use automated and highly available, you know, CI or CD systems or automated testing and good monitoring, we should expect the exact same thing for secret management. And I'm not the only one who thinks this. In 2015, there were a number of new secret management tools that popped up, things like Keywhiz, Vault, CredStash, and Sneaker. And if you take a step back and look at all of these tools, they all seem to look a little bit different. They have different deployment footprints. They make different trade-offs, whether it's in storage backend or how they do key wrapping or where they keep master keys. And it can be very difficult looking at the field to know what's the right choice for me, what is going to work in my environment, and what's going to meet my needs. And it's actually a really hard question to answer. There is no one-size-fits-all solution. Security is all about trade-offs. Your requirements are going to be different from my requirements. If you live in a heavily regulated environment, or if you run a root, you know, publicly trusted certificate authority, you are going to have very different security requirements than if you're hosting a blog about your Minecraft server. So I can't stand up here and point to any given secret management system and say, this is the one that you use every time. You have to go back and you have to understand what your threat model looks like and what your trust boundaries are. You need to understand what data you have, how you protect it, and what happens if that data can get out. So I can't stand here and just say, you know, use CredStash and you're done. That would be a really, really short talk. What I can do is we can take a step back and we can, from first principles, look at what are the problems that we're trying to solve with secret management. If I want to manage secrets in a highly automated, lights-out data center, what properties, what principles and operations does my system have to support? And we can use those properties to build a model, a little dummy secret management system to see how all the pieces fit together. And then we can use that model to compare and contrast different open source solutions and determine which one fits our needs or if none of them fit our needs. So let's do that. We're going to dive right into it. I think it's really tempting, especially in engineering, to go and, grab the cool database or grab the cool technology that you want and you build the solution, and then you kind of back out what the requirements are to justify why you're using, this crazy ephemeral Mongo database or something. So instead, I want to start with what are the principles that we want to achieve? What are the design requirements? And we'll go from there. So the first one is straight from classic information security. This is the principle of minimum privilege. Put another way, the set of actors or principals that have access to a given secret should be the smallest possible. Bob from accounting probably doesn't need the production database password. And what this means for us is that we need to have authentication and authorization on all of our usages of secrets. Now, these two terms, authentication and authorization, tend to be thrown around a bit interchangeably. Authentication is when you prove to somebody else who you are, and then authorization is what rights or what privileges you have once you've authenticated. And we really want to make sure that those authorization semantics, the list of things that you can do, is defined by policy. As time goes on, requirements are going to change, and the systems or actors that need to access a secret are going to change. So we don't want to have them baked into our system. We want to be able to change them as our needs change. And then finally, we want to make sure that we have an audit log. We want to be able to look back and make sure that we know that we've made the right authorization decisions. The next principle is that secrets expire, and sometimes this is really obvious. You have a TLS key that has an expiration date on it, or you have a session token that expires after 30 minutes, but sometimes it's not obvious. You might have some internal or regulatory controls that force you to expire a password, or you might actually have a security incident where you lose control of some credential, and then you need to rotate them. So going into this, we need to know that every single secret is going to have to be rotated. You will never, over the lifetime of your infrastructure, have something that's going to be hard-coded forever. So rotating secrets needs to be easy, and it needs to be an ordinary operation. We can't have the fire drill where we wake everybody up at 2 in the morning because we have to rotate the analytics password. And, something that shakes out of this is that secrets should not be stored in source control. This is a little bit controversial, but I feel like I can back it up for a couple of reasons. One of them is that access to your source code should not be the only prerequisite to get control of your secrets. Just because somebody can check out your repo doesn't mean that they necessarily need to have your prod database password. Also, a lot of modern source control systems, especially when you look at things like GitHub, are really optimized for collaboration and sharing, which is the opposite of what we want to be doing in secret management. This also makes it really, really hard to know what secrets you have. If it's 2 o'clock in the morning, you've just been paged, and you're trying to understand what your exposure is, it's hard to do that when your secrets are littered as const strings through a bunch of header files. And finally, having secrets in source control makes it very, very hard to rotate them. If your secret rotation procedure involves grep and sed, you're going to have a bad time. A corollary to this is that changing a secret should not necessarily require full deployment. Now, you might decide that what's right for you is to tie secret rotation to your normal CM process, and that's great if that's what you want to do. But a lot of times, secrets have different life cycles than other pieces of software. You don't want to necessarily have to do a full prod deployment just because you need to rotate a secret. The next principle is that, and we've heard this a couple times today so far, is that it should be easier to do the right thing than the wrong thing. If developers have to go through some Baroque process involving, manually filling out a request struct and serializing it and sending it over the network and then, unmarshalling the response, nobody's going to do that. We're just going to make secrets, constant strings in our source code with a little to-do comment that says replace this later, and it's never going to happen. So we need to make sure that getting secrets and working with them is really, really easy. So we want easy-to-use programmatic operations on secrets, at least for the CRUD operations, but then also for listing secrets and for auditing the usage of them. The next principle I think is really important. In general, the security of any given secret is only going to be as strong as the weakest control that you have on it. And what this means for us is that we need to make sure that we have really strong controls on every secret and on every operation of our secret. And we really want to make sure that secrets are never persisted in plain text. It does you no good if you are, spending a lot of time sending secrets over TLS, but then you write them in plain text to a text file. Now, one place where this comes up a lot is that somebody will be using a configuration management system, especially one that rhymes with danceable, and they will be encrypting secrets and sticking them into their configuration management system and then decrypting them when it's time to do a deploy. And if that works for you, great, but the question is, what do you do with that master password? If you are writing it to disk on your operator laptop, then your laptop is now part of your production security boundary. That developer laptop that, your friend installed Steam on and God knows what else is now part of the trust boundary for prod. So, think about that. Access to secrets or material that grants you access to other secrets and material really need to be kept up. The next principle, the last one, is that secrets need to be highly available. For a lot of software components, access to secrets are a prerequisite for basic operation. If my web app can't get to its database, it's effectively down. So in a lot of cases, secret management is going to be a tier 1 or a tier 0 dependency. So we want to make sure that we have really good operational deployment practices around it, and we want to be super aware of any dependencies or bootstrapping problems that keep us from either horizontally scaling our secret service or, in the event of an outage, from standing a new one up. If you build your secret service on top of your distributed key value store, but your distributed key value store needs a secret in the secret service, you're going to have a very long night. So kind of unioning up all of these principles together, we have the principle of minimum privilege. We know that secrets expire. We want to make sure that people actually use the system, so it should be easier to do the right thing than the wrong thing. We want to protect secrets wherever they go and really defend that weakest link. And we want to make sure that the system is highly available so that this thing doesn't cause us an outage. And what this means for us is that we need a system that provides all of these things. Programmatic CRUD operations on secrets, that provides an audit trail that lets us tune our authorization semantics based on policy, that protects secrets wherever they go, and again, doesn't wake us up in the middle of the night too often. So let's dig right into it. We are going to use these principles, and we are going to design a model secret management system. Now, I have about half an hour left in the talk, so it's not going to be a production-ready secret management system. It's going to be missing things like monitoring and metrics and alarming. But I'm hoping that this will illustrate what the core pieces of a system are and give us enough footing to evaluate existing systems. So we are going to talk about crypto, so if I don't include this talk, a trapdoor opens and I fall into the basement. Don't go implement your own cryptography. Don't go and read about somebody else's cryptography and, hack it up in JavaScript. You want to make sure that you're using battle-tested algorithms and, standard libraries. You really don't want the security of your whole system to be based on how well you understand an arithmetic versus a logical left shift. So digging right into it, we're going to start, as most engineering projects start, with a box in the middle of a blank screen called the secret service. And this is going to do everything that we need it to do, and it's going to be awesome. So the first thing that we need to do is attach a data store, somewhere to keep our secrets. This could be a relational database. It could be some distributed key value store. It could be whatever you like, as long as you're able to run it in a highly available mode. And when we get to looking at some open source solutions, we'll see some different options for this. And zooming into that data store, we have a structure that looks something like this. Each row is a secret. Each secret has a unique ID that's used for database-y things. We have a unique name on each secret that we can use as a programmatic handle to operate on that secret. And then we have the value, which is the secret itself. And this looks good. This is a pretty good first pass. But immediately we notice that this is absolutely terrible because we are persisting secrets in plain text. So we do the obvious thing and we encrypt them. If you're not familiar with this notation, E sub k of a value means that I'm encrypting that value with the key k. So I'm encrypting my super strong, production database password with the key k. And this looks pretty good, but if you look at it for a minute, you'll realize that we have another problem, which is, what do we do with k? What do we do with this key? Well, we could write it to disk, but then we're back to square one with, persisting secrets to disk. So we could encrypt it, but then where do we keep that key? And it turns into turtles all the way down, and, eventually we have to do something with a key. So we really have two options. We can either store the key securely some way that I'm going to hand wave around, or we can programmatically generate that key when we need it. So let's look at both of those. First, let's talk about some secure key storage. And there's a couple different options, but we're going to look at two of them. The first one is to use dedicated hardware. And in order of sort of most expensive to least expensive, we have hardware security modules. These are devices that are super, super pricey. They typically come in a 1U rack mount chassis, although there are some models that are desktop models that you connect over USB. And they come with lots of accreditations. And really, the only time that you actually want an HSM is if you know that you need an HSM. If you have an auditor that comes to you and says you will not pass your audit without an HSM, then you have to buy an HSM. Other than that, you don't use them because they're horrible. The next thing is a trusted platform module, or a TPM, and this is like a little bitty, baby HSM that's soldered directly to the motherboard. If you have a laptop that does secure boot, then you actually have a TPM, which is super nifty, and you can do some fun things on your local machine. Also, a lot of modern smartphones, like the new iPhones, actually have TPMs built into them for holding private keys for certificates. And then we have smart cards, and you see smart cards everywhere. If you have like an EMV chip-enabled credit card, which everybody in Europe does, that's actually a smart card. I checked into a hotel yesterday that handed me my room key that has a smart card in it. So these things are super, super cheap, and they're everywhere. But what all of these devices do, regardless of price point or form factor, is all of them provide some kind of hardware key storage, and then typically they provide some kind of hardware accelerated cryptography to do things like RSA or ECC at speed. And some of them, especially when you get into HSMs, also provide some tamper protection. So if you buy an enterprise HSM and you try to remove the lid, it'll detect that and wipe its memory. Or, if you are the data center tech and you get paged to go and, swap out a fan, pulling the fan out of that device will actually kick off either an SNTP or a syslog event. So they're really designed to be incredibly paranoid and kind of fragile, and if you look at them the wrong way, they wipe their memory and secrets don't get out. And all of these devices provide an interface that's called PKCS11. And this is a super cool interface that lets you either import a key into the device or generate a key into the device and use the key inside the device, but you can't get the key out. There's no export operation. So the idea is that I can say, I want to generate an RSA key, and it'll return and say, yep, key number 7 generated. And then I can send it a blob of data and say, I want you to encrypt this data with key number 7, and it'll send me the ciphertext back, but I don't get the key out. And a lot of times there's, physical hardening to prevent me from attaching leads to the device and trying to, get the key out. So this is really great, provides a lot of value for us, but generally speaking, a lot of times, especially if you use a network-enabled HSM, you still need some kind of credential or certificate to access the HSM. So we still sort of have a secret management problem here, and we're going to get to that in a few slides. If you don't need an HSM, a great alternative is a KMS. This is a key management service, and think of this as kind of like a, HSM in the sky, in the cloud, that provides a lot of the same functionality where you can generate a key inside of the service and not get it out, but you can use the key. And the trade-off here is that these services tend to be very, very inexpensive, but you don't get all of the accreditations and all of the third-party certifications that you get with a dedicated device. So if you know that you need an HSM, then you need an HSM. If you don't know that you need an HSM, you should try to use a KMS, and it'll be a lot cheaper and easier to use. The other alternative that we could do, instead of storing the key in either an HSM or a KMS, is to not store the key. We can generate it when we need it. And you can also use either of these two techniques I'm going to talk about to hold the credential that you need to talk to either an HSM or a KMS. And the first one is what's called a quorum system. And the idea here is that I take a secret, like my HSM credential or like my master key, and I split it into n pieces such that any k of those pieces can reconstitute it. The most popular implementation that you'll see in the wild is a thing called Shamir's secret sharing scheme or system, depending on who you ask. Shamir is the S in RSA, super smart guy. And how this works is it uses polynomial interpolation to stitch the shares back together. So the idea is, if you want to allow 3 pieces of your key to be brought back together and reconstitute the original, 3 points in Cartesian space uniquely define a parabola. So you define a parabola with the y-intercept going through your secret. You pick a bunch of points on it, and any 3 of those points will generate the original parabola, and you can, retrieve the y-intercept. So super, super cool. Lots of good implementations of it. And the benefit for us here is that I can split up my secret into these shares, and then I can hand them to my operators, and they can put them on smart cards. They can put them in a safe. They can tattoo them on their arm and then remove it at the end of their on-call situation. They can do whatever they like, but it means that in order for me as an attacker to compromise the system, I have to compromise multiple people. Or if I have a bad actor in my organization, it requires collusion amongst multiple operators in order to get the secret back. So this is really great for us. The other thing that I can do, and this is really exotic, and unless you need it, there be dragons. But this is called peer-to-peer induction of secret servers. And the idea is that once I've manually bootstrapped a single secret server, either by physically attaching a hardware device or by doing a quorum system, then when my next secret server comes up At boot, it can do what's called remote attestation, where it uses a TPM to cryptographically verify that it's only running trusted software. And if it can prove to the existing secret servers that it's only running trusted software, then the existing servers can hand it the key. And what's awesome about this is that you can do completely hands-off, like lights-out deployments of new secret servers, but it requires things like TPMs and remote attestation, which are super hard to get in cloud environments. So if you need this, then you're probably running your own hardware anyway, and it's hard to do, but it's pretty neat. So this is what our model looks like so far. We have our secret service, we have a secret store, and then we have our master key storage. And again, this could be a region of memory that I turn on mlock to keep it from swapping to disk, and I populate it with a quorum system, or it could be an HSM or a KMS. And one of the problems that you run into very early on if you start using HSMs is that they're miserable to work with. They are super expensive, they have limited storage, they have incredibly limited throughput. In a lot of cases, you have these same problems with KMSs. AWS's KMS, you can only send 8K to the service in order to encrypt. So if you want to be encrypting arbitrarily large secrets, or you want to have unique keys per secret, you run into problems with master key storage. So there's a technique here that we can use called key wrapping. And how it works is for each secret in the database, we generate a unique data encryption key, and we encrypt the secret with that key. And then we take that key and we bring it to the HSM or the KMS, and we encrypt that with a master key that's stored in our secure key storage. And then we store that encrypted key just next to the data that it protects. And what's great about this is it means that we can use a small number of very expensive to store keys to protect a large number of very cheap to store keys. So implementing that, this is what our database looks like now. We still have an ID, we still have a name, but notice now that each value is encrypted with a key that's unique for that secret, and then we encrypt that key with our master key and we store it alongside. Now I know there's always somebody in the back who jumps up and yells, "That's encryption, don't do that," and it's not. So encryption is when you store a key next to the secret that it protects. The important thing to note here is that without access to that master key, we cannot use K1 to decrypt the prod database password. So this is actually a safe thing to do, and when we get to existing open source solutions for key management, a lot of them do something like this. So this is our model so far. We have our secret service, secret store, master key storage. We can protect things in our secret store using our key wrapping method. And I want to be able to log things. I need an audit log of what's happened and who's accessed my things. So I'm going to write log events to either a syslog server or some third-party logging service. And the things that you want to make sure you do here are that your logs are append only, and you want to do signed logs. You don't want somebody to be able to tamper with your logs. Signed logging is really hard to get right, so don't go implement it yourself. There are signed logging libraries for every language out there. There are standards for signed syslog. I have a link at the end, so use something standard. So at this point, we want to actually have people be able to use the secret service. It's no good if all of this happens in isolation. So I'm going to attach a client to the service over some network protocol that makes sense to me. Maybe it's a RESTful API. Maybe it's some crazy RPC thing. Maybe I have that crazy guy who sits in the corner and cranks out socket servers all day. I'm going to do what's right for my organization. And I want to make sure that the service itself is authenticated. What I don't want to have happen is for a rogue secret service to pop up in my environment and start accepting secrets that it shouldn't be getting. So I'm going to run this link over TLS. I'm going to make sure that my secret service has a valid, trusted certificate on it. Months ago, this might have been a big ask, but with Let's Encrypt and AWS's certificate service out, there's really no reason why you shouldn't have, proper trusted certificates on all of your services at this point. If anybody wants to argue about that, we're getting beers later, and I love to have that argument over beers. And we also want to make sure that the client is authenticated. Network access alone to our secret service shouldn't give you access to access all of our secrets. So I'm going to do some kind of client authentication. And again, here you need to make a decision about what's right for your environment and your application. You can either do API keys and sign each request, which is what a lot of third-party software as a service vendors do, or you can generate a client certificate for each of your boxes and do mutual TLS. And there you are, assuring at the transport layer that you're only talking to a trusted client. One of the things that you need to keep in mind, whichever route you go, is you want to try to assign this notion of instance identity at either boot time or provisioning time for your services. That 12-year-old web server that nobody's touched in the last 6 years, it's hard to establish trust on that thing if you even know it's still running there. So, as much as you can, when you do your initial provisioning of an instance, give it a certificate or an API key, and that is the root of trust for that instance now. Some examples that you see in the wild are things like IAM roles for EC2, which can be kind of treated a super lightweight instance identity. Chef does some cool stuff with provisioning client TLS certificates. There's lots of examples in the wild of how to establish some root of trust on an instance. Whatever I do for my authentication token, I want to protect it. And again, this is one of those places where you have to understand what your environment looks like. There are some cases where normal POSIX file system permissions are enough. There are also some cases where you really need to start delegating key management to the kernel. There's actually a kernel key retention service that lets you do really fine-grained semantics about who on the box can request keys. Maybe you want to turn on some kind of mandatory access control system like SE Linux or AppArmor. Do what's right for your environment. So at this point, we have our secret service. We have a store to store data. We have a master key storage repository somewhere, whether that's an HSM or somewhere in memory that we use to protect those secrets. We can log off events in a secure way. And we have a client that can talk to us over an authenticated link. So we're finally at a point now where we can start doing operations. We can start actually using this thing. So the first operation, secret storage systems aren't really interesting if you can't store secrets, so we need a create operation. And here, when you do a create, the system needs to do your access control check. It needs to log off the result of that access control check. And then we're going to do our key wrapping. So we take the secret that was created, we generate a unique data encryption key for it, encrypt that secret, encrypt the data encryption key, store that, and we're good to go. And if there's any initial access control policy that we want to do, like setting a group that owns the secret, something like that, we do that at this step as well. Reading a secret is exactly what you would imagine. We do the exact opposite of create. We unwrap the data encryption key. We use it to decrypt the secret, and we send it back. We also make sure that we do access control checks and log those off. And then update is where this starts to get interesting, because the naive thing to do for update is when you update a secret, you treat it just like a create, and you overwrite the old value. But one of the most common things that you'll use secret management systems for is to hold encryption keys. And if you have some long-running process or some workflow or you have some archival data that's encrypted and you overwrite that encryption key, you've effectively destroyed access to that data. So we're not going to overwrite the value. Instead, we're going to add a new version. And in general, secrets should be versioned and immutable. Once you write a secret into the secret store, you never change it. You just add new versions. And so this is actually what our API starts to look like now. Whenever I do a create, I'm actually doing an update, but I'm setting the version to 1. And we can do some cool things in our API or in our client utilities to make sure that if I request a secret without providing a version, then you'll vend me the latest one. But what's nice about letting people ask for a specific version is that if you have a long-running workload that goes over weeks or months or years for some crazy analytics job, you can pin that workload to a specific version of a secret so you know that you don't lose access to that data. It's kind of like versioning your dependencies. You want to be able to pin processes to the secrets that they depend on. So implementing that, this is what our data store now looks like. We still have an ID, we still have a name, we still have our encrypted value and our wrapped data key. But now notice that we have a version, and every time that we've updated the production database password, we've actually added a new version of it. And this means that, again, if I have that long-running workflow, I can say, you are pinned to the prod database password version 2. And this lets us do things like manage migrations very easily. You don't have to have everybody jump at the same time. Delete is the other interesting case because a lot of times, again, if you have some long-running workflow, you don't want to delete the secrets out from underneath your workers' feet. So frequently what you see in the real world is deletes are logical deletes. You'll have a field in the database that's called is deleted. And if that's true and you request that secret, then it returns an error, but you still have access to that secret if you really, really need it. Now, there are times like when you'll have a compromise and you actually want to delete that. So you might have a force flag, or you might have a x- no, I really mean it, HTTP header that you include with the request that'll actually delete it. We also want to have a list operation. One of the big secret management systems just added list very recently. I think this is super important, especially when you start talking about service discovery and environments where you have your services come up and learn about what's available to them and connect. Being able to do a prefix list or a list is super, super handy. And then finally, the last fundamental operation that we need is we need to be able to control authorization policy on these objects. So we want to make sure that we can change what users or groups or systems have access to individual secrets. And whenever I say the word policy, people tend to groan or their eyes roll into the back of their heads because they imagine like IAM policy, where you have this crazy JSON object that has like resources and actions and conditions and principles and has to be evaluated at runtime, and it's just a mess. And that is policy, and if you need that, then you should do it. But policy can also be a Boolean. I might just have a set of flags in my database that says Alice is allowed to access this secret, but Bob is not. And that's policy, and that's tunable at runtime. So you need to decide what level of policy granularity you actually need. And then one thing to really point out here is that being able to change authorization policy is a privilege escalation vector. So a lot of times it makes sense to have policy controls be through a different interface or require different credentials so that, you know, your compromised web server can't go and like give itself star.star permissions. So implementing that, we have sort of the traditional control plane, data plane split. So we have a control plane where an administrator, usually a human operator, can log in and change policy on objects or groups of objects. And then we have a client interface, our data plane interface, where our machines can actually use these secrets. And again, we want people to actually use this system, so there's a few considerations that we want to make around interfaces and libraries that we vend to our developers. A few things are we want to make sure that our clients aren't leaking secrets. You know, think about your logs, think about core dumps if a process crashes. You really don't want to log into your syslog server and see plain text passwords. It kind of defeats the whole purpose. And again, people are going to do whatever is easier, so if you have a verb that's just get secret, people are much more likely to actually use the system than if it involves, you know, complex marshalling and unmarshalling of a request object. I want to spend a few minutes talking about availability because, again, secret management is often a very, high tier system. So we want to make sure that whatever your unit of fault tolerance is, whether that's, you know, an availability zone or a data center, if you're running your application multiple places, your secret management service needs to run in all of those places too. You don't want a single data center outage to cause an outage for your whole application because nothing can get to its secrets anymore. So running in multiple AZs or data centers makes a lot of sense. We also want our secret servers to be close to clients, not only for fault tolerance, but also for performance. You know, reducing latency on a call that's in the request path is super important. Whatever data store you pick needs to be highly available, and we need to make sure that we're aware of bootstrapping problems if we need to stand up multiple of these. And then finally, I didn't really have time in the slide to really get into system hardening. That's a whole other talk. But if ever there was a time to grit your teeth and actually turn on SE Linux and configure all of the booleans and all the file system labels, this is the box to do it on. And we definitely want to make sure that we have good operational metrics. We want to have canary clients that make requests to this thing and bubble up metrics around request latency and error rates so that we see problems before they come. We want to have good integration tests if we're actually writing code for this, code reviews, and your summer intern who's here for 6 weeks probably doesn't need to be able to push to rod on the secret service. So keep in mind who can actually put code into this thing. Now, depending on your security model, you might be able to get away with some client-side caching. You can either do this as just a straight write-through cache, or you might be able to take advantage of a publish-subscribe model where your clients subscribe to the secrets that they care about, and then whenever one changes, it gets pushed down to the client and cached. Now, if you can get away with this, then it actually puts you in a really good place because it not only reduces latency to fetch secrets if your cache is hot, but it can also help you with availability issues in the event of a network partition. If you lose connection to the secret service, but you have your most recent secrets cached, then you're actually not in too bad of a place. If you go this route, though, then you want to make sure that your cache itself isn't leaking secrets. What happens when that thing core dumps, or how does that log? And you also need to look at what your security model looks like on your actual box. Is each instance, dedicated to a single workload, and your security boundary is the instance boundary, or are you running mixed workloads on a server? Are you worried about a low-privileged user being able to hit the cache and retrieve secrets that are populated by a high-privileged user? So if we roll out caching, this is what we end up with for our model. So we have our secret service that can store secrets in its data store, can protect them with master key storage, can log off requests. We have an administrative interface for manipulating policy, and we have a data plane interface with a client that does some caching. And this looks really simplistic. We're missing deployment, we're missing monitoring, we're missing lots of stuff that you'd actually want to see in production. But these I assert, are the fundamental pieces of a modern secret management system that's going to survive in a highly automated environment. In a minute, we're going to look at some existing open source tools, and under the hood, most, if not all of them, look just like this. There are a few cases, like with CredStash and Sneaker, where there's not a single secret service. It's kind of broken up, and those roles are distributed to other pieces. But fundamentally, these are the operations and the core pieces that all secret management systems have, and we can use this model to compare and contrast what the trade-offs are that these different systems have made. So let's look at some existing tools. The first one that I want to talk about is called Vault. This is from the fine people at HashiCorp, purveyors of things like Vagrant and Packer and I think Terraform, right? And this is a client-server system for secret management. It looks a whole lot like our model. What they do for secret storage is they have a pluggable backend system. So they've supported disk and console, which is their distributed key value store, from the start. I saw a blog post that they also added recently, like a DynamoDB driver, but when I went to pull up the docs, I couldn't find the documentation. So, definition of done, it doesn't exist yet. They do secret splitting using Shamir's secret sharing scheme to protect their secrets. So when you first stand up an instance of Vault or when you reboot one, it comes up in what's called a sealed state, and then your operators present their shares of the master key. They get reconstituted, and the Vault is now unsealed, and you can do operations with it. They use either symmetric tokens or TLS client certificates to have clients authenticate and do secret operations. They have a JSON-like language called HCL that you use to author policy on your secrets. You can use them via CLI or an HTTP API, and they have one super nifty feature that I really, really love. It's called dynamic secrets, and the idea is that you can have Vault go and configure like AWS creds for you, or they can go and generate a password in your database for you, and then vend it via Vault. So you can kind of unify all of your third-party credential management into the system. Another system that came out of Square is called KeyWiz. Again, another client-server system. And here they actually use a relational database for key storage. So if you're using Console with Vault, then you're doing kind of the distributed, eventually consistent key value store thing. Here we're using MySQL or Postgres. And they do something a little bit different from key wrapping. It's very similar, but it's a little bit different. It's called HMAC-based key derivation, where instead of storing a master key and then encrypting each data key with that, they store what's called a derivation key in either an HSM or live in memory. And then whenever you need a data encryption key, it generates it from the derivation key using a series of HMACs. So you're kind of going the other direction. Instead of generating a key and then protecting it, you are starting with your protected key and then generating keys as you need them. They use client TLS certificates to authenticate for CRUD operations. So if you want to use KeyWiz, you need to have a CA in your environment. Maybe that's super easy for you because you already have some kind of enterprise certificate authority. If not, they have a lot of tutorials on how to stand up a quick and dirty CA. You use either LDAP or passwords to authenticate for their administrative operations, like authoring access control lists. Their ACL semantic is based around groups, so you might have a web server that's in the web group, and it can access the database password. And they have a CLI and API, and then they also have a super sweet Fuse driver that lets you mount your secret space as a virtual file system on your box. So any tool or system that you have that can read and write files can interact with KeyWiz. It's super awesome, and I'm jealous of it for my project. The next tool is called CredStash, and I have particular affinity for this tool because I'm the maintainer of it. So if anybody likes Python and secret management, we are taking pull requests all the time. And this is a super lightweight Python utility, but also a library for managing secrets if you're running on AWS. So this is the first one that's a little bit different from our model. We don't have a centralized secret service. Instead, we take all of the operations that you need in a secret service, and we distribute them amongst a bunch of AWS services. So for example, we use DynamoDB as the authoritative data store for holding our secrets. We use AWS's KMS to hold master keys, and we use them to do key wrapping. We use AWS's IAM service, which is their kind of permissioning and access control system to manage permissions on all of these things, either on database rows or on the actual keys. And you can use CredStash either via CLI, a Python library, or there are Puppet and Ansible modules. The Ansible module actually ships with Ansible. So if you're using Ansible, you can do a CredStash lookup from your playbook, and it'll just hook up to CredStash, which is super cool. And then also, in the last few weeks, people have ported CredStash to Node.js, PHP, Go, and a bunch of other languages. So if you want to use this, there's probably a library in your language of choice. And then the last tool that I want to look at is called Sneaker. This is from Coda Hale, who always puts out amazing pieces of code. And this is very, very, very similar to CredStash. It actually was released a few weeks before we were able to open source CredStash. Very similar thing, but it uses Go instead of Python, and he uses S3 instead of DynamoDB. So DynamoDB and CredStash are very much like a key value semantic for keeping track of your secrets, whereas Sneaker uses more of like a file semantic because it's putting stuff in an object store. So I would play with both of them and see which one makes more sense for you. All of these systems, though, are really new. All 4 systems that we just looked at all came out in 2015, or at least were open sourced in 2015, which means a few things. One of the things that it means is that all of them are looking for contributors. I think all of these projects are Apache 2 licensed, so if you have the ability and the inclination to work on this stuff, then definitely get involved. It also means that there might not be something out there right now that fits your needs perfectly. You might have to write a little bit of glue code, or in some cases, you might actually have to roll your own system. But I hope that I've impressed on you that there are a lot of considerations to think about when you build a secret management system, and writing one from whole cloth isn't something that you should just dive into willy-nilly. You really need to understand your threat model and your trust boundaries. Rolling your own system is hard, and getting started with any of these existing systems are really, really easy. If you're already running on AWS and you're okay with the trade-offs that we've made in either CredStash or that Coda Hale made with Sneaker, then you can get up and running with either of those 2 solutions in about 10 minutes. If you actually need to use an HSM or you're running something on-prem, then maybe you should look at something like Keywizz or Vault. But I would definitely consider, looking at these systems in the light of your own trust boundaries and threat models and trying to understand if any of these things fit. But regardless of what you do, I hope that you agree that secret management needs to be part of infrastructure. We need to get away from people checking secrets into GitHub, and we need to have people actually, easily and robustly treating our secrets so that we can protect our businesses. So this is kind of a huge topic, and I know that I blew through stuff. So the slides are up on SlideShare at this bit.ly link. And if you download them, the very last slide has some links to some further reading about things like KMS and remote attestation and lots of other cool things. So go check it out. Let me know if you have any questions. And with that, we can do a little bit of Q&A. Or a lot of bit of Q&A. We have like 15 minutes until coffee.
So are there any questions for Alex?
That's what that looks
like. Thank you for the talk. Imagine we have a company that doesn't use any of that, and how can we start with any of those systems? How can we apply it? And
Yeah. So the question, as I heard it was, if I'm not doing anything right now, where do I start? And what I would say is, pick one system, something that's kind of out of the critical path, and game out, prototype what it would actually look like. Do the whole thing, and see how that works. Socialize it, shop it around. At my current company, so I wrote CredStash at Fugue to handle our own credential management needs, and we initially used it just for our continuous integration system. So the idea was, you check something into GitHub, the CI system wakes up from its long slumber and goes and builds everything, and needs to push out deployment artifacts to our artifact repository. So we wanted some way of handling those credentials, and so we started sort of full-blown credential management by putting them in CredStash and seeing how that worked, seeing what features we needed to add, and then we gave brown bags and said, hey, everybody, we should all be doing this. And that's kind of how it grows. I think, this notion that you're going to do a whiz-bang, all of a sudden one day, you flip on secret management and everybody's using it, is an illusion. It's never going to happen. So I think the best thing that you can do whenever you want to try to institute large change in any reasonably sized organization is to pick somewhere to start, do it as completely as you can, and then show people why they should do the same thing. I always say that working code beats high-minded rhetoric every day. So, sitting down in a meeting and yelling at people about why we should protect secrets is kind of effective. Showing people, look how easily I protected our business's secrets. Like, it took me less code than storing it in this, plain text MySQL database, and like, look how easy it is. And then everybody will say like, oh my God, that's awesome, and go do it. So it's tricky. You can either do it by mandate or you can do it by showing people that there's a better way. And I think a lot of times showing people that there's a better way is pretty effective. I see a hand in the back. Or you're just waving.
One of the things you just have mentioned is usability. I think we all have seen that with Let's Encrypt project, rolling out certificates thanks to new protocols it's going to become more popular, or at least to get a wider adoption. Even some tools like Kodi, the new web server, automatically generates all the certificates and everything. You don't have to put that in your configuration code or anything like that. So, in my opinion, usability it's key for wide adoption of security for this kind of infrastructure, or to have security as part of your infrastructure design. What do you think it's going to be the usability steps required to approach to a wider adoption?
Yeah, so usability is like one of the most important parts of this, because if nobody uses it, then like all that we've done is, put human sweat and misery into one end of the machine and like outputted a bunch of heat, right? Like we want people to actually use the system. So that's why things like, a Fuse file system driver are so amazing. Asking somebody to implement a driver for your homebrew, binary on the wire protocol is kind of a big ask. Saying, hey, can you read a file on the local box is like not a huge deal. And so I think things like Fuse drivers, one of the reasons why with CredStash we really wanted to have it be a command line client is so that if you are standing up a service in like an init script, you can execute CredStash and just stick the result of it in an environment variable. And saying to a Django developer, hey man, I'm putting the database password in your environment. Can you read that? Like, if the answer is no, then you have other problems other than, like secret management. So I think usability is super important. I think one of the things that's very important is to look at your existing environment and how do your components get their current configuration. If somebody has already done all of the work of, plumbing database endpoints into the system, whether that's through environment variables or, some YAML file that gets generated by Chef or like whatever you do, if you can kind of latch onto that with your secret management system, then it's going to have much less friction getting this rolled out across your whole environment.
Wow, 4 at the same time. We'll start with Matthias then.
So one stack of turtles that I'm struggling with in this is outside of Amazon, where Amazon attests that this machine is what it says it is. How, like on bare metal, how can I get a machine into this so that I cannot, as a developer, just get myself a machine that claims to be the app server and get the database credentials and slurp it all down.
Right. So that initial step, I called it a root of trust, and I think that's like a very... So I picked that term specifically, right? Because if you have some cryptographic guarantee that a machine is who it claims it is, you can do lots of stuff. But if a developer can like log into their laptop and say, I'm a prod database, then it all goes out the window. So there's a couple different things that you can do. If you have... So one of the traditional ways that you solve this problem is that you have some side channel to verify a claim that a machine is who it is. So say that you do, and I don't know anything about your environment, but if you are programmatically provisioning things, Rat comes in, you scan the barcode, you plug it in, and you say like provision as web server. If the web server comes up and says like, hi, I'm 192.168.1.1 or 1.2. I'm a web server. If a certificate authority or some kind of entitlement service can go and verify in your provisioning database that, like, yes, a machine with this MAC address, with this web server, was just powered on and should probably be a web server. That doesn't completely cover you because there's, always that crazy edge case where, like, an attacker, like, waits until you plug the thing on and he, turns his on at the same time. But, we're adding layers of complexity here, right? Like, if an attacker is able to compromise your configuration database and your entitlement service and can get in your data center, then they can bootstrap something with proper instance identity. But if they can do all of those things, then all bets are off anyway. So it kind of depends on what your environment looks like. But in general, if there's a out-of-band mechanism that you can use to, say like, oh, yeah, I do have a database server like in that rack, then that gets you a long way there.
Thank you. I thought we had another question here in the back. Whoa.
How do you recently assess TLS security and CA fraud? Because I guess this is also part of the secret management infrastructure.
Yeah, so, so like CA trust issues are kind of a rabbit hole. If you launch, a relatively modern operating system and look at your list of like built-in root CAs, there's like a, where was it? There's like a library in Japan or something that's a root trusted CA. That doesn't make any sense. So if you're worried about something like somebody breaking into this Japanese library and misissuing certificates, then an earlier step is you need to like own the contents of your trusted CA store on your systems. Now, that's hard to do on client machines, right? Like you want your laptop to be able to go to a website and for TLS, to work most of the time. But on your production servers, there's probably only 2 or 3 root CAs that you actually trust, right? Like you might have an internal CA that you trust and you've already imported that CA certificate. You might have, something like a VeriSign or a DigiCert or, a global sign or something that you trust because, your apt repo has their, TLS cert signed by them or something. But out of the 300 or so CA certificates that ship with the OS DVD, you probably don't need most of them. So I would throw out a bunch of those and whittle it down to the ones that you actually want to trust. In terms of TLS security, there's been a lot of issues recently with like OpenSSL vulnerabilities, that kind of thing. I don't have a great answer for that. We haven't really found something that's as widespread and works quite as well as TLS that's, as ubiquitous. So, I mean, like, patch your systems and hope that there's not some zero-day out there. I realize it's a really unsatisfying answer, but, like, at some point you have to trust something. I don't know.
More questions?
Yep, right there.
Oh, hey, it's related to what the other questioner asked. You said that secrets expire, and if you can detail a little bit why they would need to expire, because sometimes they need to expire after a period of time. And there's also this distinction between secrets stored on infrastructure that you directly control, and you can modify them directly, you can annul them directly, or in case of CA, when you've got a certificate, you cannot revoke it that easily, right? So would a good practice be to institute a short period of secret expiration if you can reissue a new certificate and just forget about the revocation problem?
Yeah, so there were a couple of questions in there. I'm going to answer them out of order, so if I miss something, like, let me know. With sort of short certificate lifecycle or lifespan, that's actually a really common and interesting strategy that's being used, especially by more and more CAs. So somebody mentioned Let's Encrypt earlier. Let's Encrypt is an awesome example of this. So if you are running a publicly trusted root CA, one of your biggest cost drivers is the size of your certificate revocation list, because it has to contain every single cert that you've ever revoked ever. And anytime not just one of your customers hits you, but one of your customers' customers hits them, it fetches this CRL. And so a multi-megabyte CRL that you have to host becomes a huge cost. So for a CA, what you really want to do is minimize the number of certificates that get revoked. And you can't just say, like, we don't revoke certificates, because that's like a jerk thing to do. So what Let's Encrypt is doing, for example, is they only issue, I think, 3 or 4 month certificates. And the idea is that, if you lose control of your private key, but you only have a week left on your cert, then maybe you won't revoke it. So having short lifespans for secrets and just issuing them more frequently makes a lot of sense. Where that breaks down is that there are some secrets, like in sort of pre-Let's Encrypt days, getting a TLS certificate, especially if you look at like one of the extended validation certs that gives you like the green bar in the browser Chrome, involves a lot of human process. You have to, send proof to the CA that you are from the company that you claim to be, and they have to verify that it's a real company. It's not something that you can just wrap in a shell script. And so, for secrets that involve a lot of human hand-on keyboard time, a lot of times it makes sense to have them be longer lived, but they're still going to expire at some point. I mean, even root CA certificates expire after like 30 years. So, at some point in your infrastructure, you're probably going to need to rotate things. So it's just a good practice to assume that everything's going to expire, and that way you don't get lazy and just like hard code things as strings. I think I answered most of your questions. Great.
All right, then it's time for another coffee break. But first, thank you, Alex.